Okay, everyone. Here's an interesting scenario, I think, regarding the problems that we have done in person and that you've also seen in video form. You've seen some sort of video form of film form of something like topic 4 from the Serway book, page 118, problem 73. There may have been another problem that I had done at some other time that was very similar to a problem like this. So there's a video form of that, there's a film of that, and there's also a film specifically on this problem. So I think I'm almost sure that in more than one place we have a problem similar to this. I did this exact problem in a film that you'll have to which you'll have access, and there was similar problems to this that I've done in other circumstances and on film as well at other times. Not this exact problem, but similar to it. Again, as I said, in addition to this exact problem. Let's kind of look ahead a little bit and look at energy considerations and what goes on with energy considerations. What is the proof of any kind of solid mathematics that's going on? Well, if the mathematics is consistent in all instances, if you're trying to solve a problem and you're using mathematics, the mathematics has to be something that gives us what we want to find, and that is correct answers. Regardless of how we're approaching a particular problem, we may approach it in numerous different ways. If the problem has a solution, we better be getting the exact same solution regardless of how we're trying to solve the problem. Earlier in this exact problem, we were able to find out what the acceleration was. We looked at two different scenarios. If there's friction present and if there's not friction present. Well, let's do the harder scenario, guys. Let's look at the one with friction present and do it another way and still get the exact same answer. Well, that's pretty interesting. I've got a lot of stuff written up here, and I'll probably end up erasing some stuff just to finish off the problem. But let's talk about it relatively quickly, guys. And we can always talk about this in person as well, obviously. Let's talk about energy considerations, not worrying about, let's right now not worry about tension 1 and tension 2, T sub 1 and T sub 2. We already know how to solve for T sub 1 and T sub 2, and we can certainly go back and solve for T sub 1 and T sub 2 and get all the answers that we want to get. The thing that gets us to solutions of T sub 1 and T sub 2 is, can we find the acceleration that is taking place here? Now, we were able to find the acceleration in earlier examples of problems looking like this, and in fact, in a problem that is exactly this, that I've done in at least one other film, right? We've been able to see how to get what A is, what T sub 1 is, what T sub 2 is. We had to find what A was in order to find T sub 1 and T sub 2. And we found what the acceleration was through all the tug of wars that were taking place. And I've left it up here unchanged. But now let's kind of like make up a problem. Let's say, could we do this another way? Well, let's do it. And like I said, if we don't have all the energy considerations under control right now, in the lecture we'll get there, and this will make sense how we can use energy considerations to solve a problem like this. Let's make a very long story short, I guess you could say. We already know how this thing ends. This thing is altogether as one large mass, M1 plus M2 plus M3, one large mass equaling M1 plus M2 plus M3, is all going to move on this side upward, on this side to the left, and on this side downward. It is going to be going counterclockwise. We know that. We proved it specifically here. As I said, in other places, probably a long time ago, I know I've done similar problems to this, both live and on film, that are just like this. So they're there for us. And so obviously have other teachers done the same thing in various instances. Great. We know how to solve this problem. The tougher scenario was when friction was present. So let's go with friction present. Tell you what I'm going to do. I'm not going to worry about the tensions. I can solve for them. But I'm going to say this. I already know this thing's going to go counterclockwise. When it goes counterclockwise, this large mass M sub 1 is going to fall a distance h in a particular time period t. small t. It's going to fall a distance h. They're all at a dead stop. They started at a dead stop. If they started at a dead stop, you guys, V sub I is 0 meters per second, how it all started. You're just holding on to the system. You're holding it, you have your hand on it, or some machine is holding on to this, and the machine releases this, and everything goes counterclockwise. There will be a final velocity after a period. I mean, let's say these ropes are very long, very light. The cables are very long, very light, massless. The pulleys are massless. They're very long. The table is, let's say, very huge. So you're never going to run out of rope. You're never going to run out of room to fall when this is going on. So let's give ourselves that scenario. Initially, it starts at 0 meters per second. It'll end at a final speed of v. V sub f will be v. We know, kind of keep it in the back of our minds, that the distance it'll fall is h. The distance it moves sideways is also h, because the ropes don't stretch. And the distance this will rise, this mass right here will rise a height h. This mass right here will go to the left a distance h. So this mass will rise a height h. This same mass will also move a distance h to the left, and this mass will fall the same distance that the other ones moved, a distance h. There will be an increase in potential energy experienced by this mass. This guy's potential energy doesn't change, but it's moved through a distance h. It's fighting friction, so it's going to create thermal energy. So this whole process, energy is going to go into overcoming friction and creating thermal energy. So energy is going to be expended to do what it does here. Energy is expended to make this thing climb, and energy's put into the system to make this thing climb. Energy's put into the system to make this thing move over, to give you thermal energy, and that's really done by this guy falling. It loses. This guy falls this much. That means it did a lot. I mean, it doesn't balance out completely. They don't come to a dead stop, but this guy gained potential energy. This guy had energy expended to heat up the surface. So energy was put into here to rise it and increase its potential energy. Energy was put in here for thermal energy to be manifested. And that happened because this guy fell. While he fell, he also sped everybody up. So he gave this much potential energy. He gave up this much potential energy so this guy could gain potential energy, and this guy could have work done against friction to heat up this environment. So raise potential energy, do thermal energy here. That happened because this gave up potential energy to do those two things and to speed up everybody. Everybody ends up moving. So this guy did a lot. This fall down did a lot of work. Well, we know that initially everybody started at 0. You went to VF. The distance h traveled is VF plus VI divided by 2. It's the average between the two. Times, this all took place in a time period t. Let's talk. Let's kind of go roundabout on this thing. As we said, VI is 0 meters per second. VF is V. If you add, we all know that the average speed is the high and the low added together, divided by 2. The average of the high and the low is the average speed if there's a constant acceleration going on, and there is a constant acceleration going on. We can go into that some other time regarding this, but it looks like everything that we're dealing with a gravitational field that's not varying. So what's being powered here, how this whole thing is happening, there's no variable acceleration taking place. It's reasonable to say there's no variable acceleration taking place. It'll go to a final speed v sub f. I'll say v sub f is equal to v. It's a little easier to look at than v sub f. And v sub I is 0, because everybody started at 0. V sub f plus v sub I, the high and the low added together, divided by 2, times the amount of time this motion is taking place. Average speed times time will tell you the distance h that it fell, the distance h that it went over to the left, and the distance h that it climbed. Everybody went a distance h because everybody is tied together. I'm not looking at force considerations here. I'm looking at energy considerations. Now, we know that VF is VI plus AT. Some kind of acceleration took place. Well, VI, it started at 0, so VF equals AT, you guys. VF is equal to AT. VI is 0, VF is some V, and that VF being AT is an interesting point. If VF is AT and VI is equal to 0, what do we got here? Well, VF, we said, is VI plus AT. VI is 0. So what we have here VF equals VI plus AT. So VF is, well, VI, well, let's put it this way. VF is just AT. VI is 0. VF plus 0. VF plus 0 is just the VF, divided by 2 times T will give you the distance traveled. H equals AT over 2 times T. Well, why don't you multiply that out? Dividing by 2 is the same as multiplying by a half. 1/2 AT times T. 1/2 AT times T. T times T is T squared. So you got this, you guys. H equals 1/2 T squared for the way this thing is falling. And again, there's different ways this has been manifested, and when we talk in person, we can talk about it. Let's come to this in a second. Can we do the bookkeeping? If we can do the bookkeeping, we've always talked about, or we've already talked about, energy is conserved. If you can account for the energy, you can set up a good equation. Initially what's going on in terms of energy, and finally what's going on in terms of energy, we can set them equal to one another if we're very careful in our approach, because energy is conserved throughout the universe in its various forms. Energy in its various forms is conserved throughout the universe. We also said that linear momentum is conserved throughout the universe, and we also said that rotational momentum is conserved throughout the universe. Simple as that. We've said that. Now let's get back to the energy conservation. Well, I'll tell you what I'm going to do. What do you say? We're not sure what's going on here, but we are, from the past experience that we had with this exact same problem, from the past experience that we've had with this exact same problem, let's say a couple things. Well, we know that initially we were holding on, or there was some machine holding on to this system in some way, shape, or form, and nobody's moving. VI is equal to 0. There's no acceleration and there's no initial speed. Everybody's at rest. Or if I'm holding it, everybody's at rest. If I let go, everybody starts moving in a counterclockwise direction. If there's an acceleration, they will keep gaining speed. Well, yeah, indefinitely. Let's say these ropes are very long, very light, the pulleys are frictionless, the table is huge. This thing could fall for hundreds of meters if we designed an experiment that big. It could fall for hundreds of meters. It could fall for, who knows? I mean, I don't know how outrageous we want to make this thing up, but we could make this theoretically in some potential gravitational field, in some gravitational field that we could talk about. We could make the table as huge as we wanted. This stuff could be moving for miles for all we care, if the ropes are long enough and everything. Now, the ropes have no mass, the pulleys have no mass, there's no friction. The only place there is friction is between the ground and is between the table and M sub 2. The frictional force that is being offered is mu sub k m2g. We've already talked about that. If this force has to be overcome, you have to have a force exerted on it that overcomes this, that is equal to this, at the very least. And even more than that, if we're going to have more things happen. I don't want this thing to be a dead heat. I want this thing to end up accelerating. And we know there is an acceleration taking place. But for what's going on right now, there's a frictional force F, And how much work are you doing against friction? Well, didn't we say force times distance? Force times distance is going to be work. The frictional force times distance is this. The work that you have to do to overcome friction, friction is mu sub k m2g over the distance d, my friends, is h for our purposes. It moves a distance h. You have to overcome it. Don't worry about positive or negative right now, as long as you account, well, let me take that back. Absolutely worry about positives and negatives, but give a strong setup and you'd be amazed how little you have to worry about formalities. I understand that the work done by friction is a negative work. I get that. How about I just take it another way? The work that has to get done to overcome friction is a positive amount of work that this falling down massive entity, or relatively massive entity, 4 kilograms it is, as opposed to 1 kilogram and as opposed to 2 kilograms. The falling down it's got to do work to overcome that friction. It's got to do a positive amount of work to overcome that friction, and friction itself does negative work. Let's not go around in circles, you guys. We're not going to worry about going around in circles. The thing is, we're just going to say, look, mu sub k m2gh is the amount of work that this falling down guy, he's kind of the motor. This one is the motor to everything. This guy's the motor of everything because it's the strongest one there. It's going to make it happen. So what's going on? Let's be careful. What's going on here? Well, I'll tell you what I'm going to do. You could do this a bunch of ways, I guess you could say. That big guy, M1, has a force associated with it because it's in a gravitational field, M1g. That force, M1g, is being put through a distance h. M1g is force, h is distance. Force times distance is the work that M1g, that's just what I said. Let me say it, forgive me guys, let me say it again. M1g is the force being applied through a distance h. Force times distance is the work associated with what M1 does because it's being pulled by a gravitational field. M1gh is the work that this thing has done. Okay, tell me more. Well, if this guy is the thing, kind of the motor for the whole thing, what did M1gh, what did M1 accomplish? It accomplished M1gh of lost potential energy. That lost potential energy, that fall down of h, associated with a force being applied over a distance h, the force M1g applied over the distance h, that force M1g applied over the distance h is the amount of work that it has done to everybody. What does that mean? Well, all this work went to a number of places. First of all, after it fell a distance h, it took a time t to fall a distance h. At that moment of time t, when this guy fell a distance h, after a time t, everybody attached to one another, m1 plus m2 plus m3, 1/2 mass times velocity, magnitude of velocity squared. 1/2 times the total mass times the speed squared is the kinetic energy that the system has after this fall down happened. In addition to that, that fall down also picked this guy up, gave him potential energy, M1gh, that it did not have earlier. This guy falling down h, with the force M1g applied to it, did the following. After t seconds, the M1 fell a distance h. After t seconds, everybody moved h. This guy fell, lost potential energy in the amount of the force M1g times h. M1gh is the potential energy that was given up by this relatively massive object. Where did that potential energy go? It gave kinetic energy to the whole system. 1/2 mass v squared. 1/2 mass velocity squared. Well, the total mass is this. It gave kinetic energy. It also gave potential energy to the lighter mass. And it also gave heat energy to the system in the form of overcoming friction to the amount friction times distance traveled. Mu sub k m2g is the frictional force moved through a distance h. So the thermal energy generated overcoming friction, the increased potential energy of m sub 3, and the increased kinetic energy of the whole system all happened because this guy fell down. That's how you account for it. That's kind of neat. That's kind of neat. Well, let's write some stuff if we can. Well, I'll tell you what I'm going to do. Why don't we subtract m3gh on each? Why don't we subtract m3gh on each side? Subtract mu sub k m2gh on each side. So m3gh is subtracted on each side. Mu sub k m2gh is subtracted on each side. And wait a minute. There's a gh here. There's a gh. So you're subtracting this on each side, you're subtracting that on each side, so that's going to be by itself. This stuff up here is going to be all by, you're going to leave that guy alone. I want to leave that alone. I want to subtract this on each side, and I want to subtract this on each side. They go, it comes over here. Well, wait a minute, there was a GH right here. I left that guy alone, as we said. This guy got left alone. We're going to deal with him in a little bit. Got left alone. And I subtracted m3gh on each side and mu sub k m2gh on each side. And there's also a gh here. There's a gh here, a gh here, and a gh here. Subtracted this on each side, subtracted that on each side. And then I'll do that on each side and then factor out the gh that's present in all these. I get down to here. Then I said, okay, guys, so we got it to here. Let me kind of not start just so we don't confuse this stuff. Okay, so that's from all this. So this was this is with all that. You subtracted this on each side, and you subtracted this amount on each side, you subtracted that amount on each side, and doing so, there's GHs everywhere. They factor out over here, and but don't put it with this one, guys. Forgive the yeah, not this one. It's just this right here. Not this guy, because you subtracted these two on both of these. This sum, you subtracted this sum on each side from here, subtracted it on this side, subtracted it on that side. So he's done, bam. And that's where the M1GH, this guy, M1GH is by itself, M1GH minus mu sub k M2GH minus M3GH. Factor out the GH, you got this. That's from this right here, you guys. That's from this right here, just this. Multiply by 2 on each side. It looks like this. Let me take the 2 down to here, and I got 2GH. That's starting to look kind of familiar. Then I'm going to take, what do we say V was? V was the VF, and the VF is AT. The VF is the V. So the VF is the V, and we said that the V is AT. VF is AT, which is the same as V equals VF equals AT. V is AT. Take the quantity AT and square it. You got A squared T squared. This guy stays here. V is AT. V squared is A squared T squared. T is the time it took to fall H. Climb H and slide H. They all moved H. This guy climbed H, gained potential energy. He had to get the energy from that guy falling. This did all that thermal energy was manifested. That also got it from this. And they're all moving. And that also happened from this. So this guy right here, this M1GH powered everybody. Gave kinetic energy, raised the other one's potential energy. This drop in potential energy gave kinetic energy to everybody, gave kinetic energy to the lighter mass, and did thermal work. All of that happened from him. We got these over to that side by doing algebra. So subtracting over here, and that got us with this guy staying as is, as we said, and we got M1GH minus mu sub k M2GH minus M3GH, and factor out the GH. And that's where this all comes from, guys. You got to be very, very careful how that plays out, how we're looking at that. Then you multiply by 2 on each side. I'll put the 2 right next to this guy. We'll talk in a little bit. We said that V was equal to AT. So V squared is the quantity AT squared, which is A squared T squared. T is the amount of time for all this to move, the whole system to move a total of H. You give it more time than T, it's going to move a longer distance than H. It's going to keep moving. It might move 10 times H. Let's say it will move. I have enough room for it to move. It's a very big experiment. It's huge. This stuff can fall hundreds of meters. Who's to say? This can, hypothetically, you can set this up any way you want for as big as you want, miles if you want, kilometers if you want, whatever. Falling. The more time you give this, the more distance H will be manifested if the circumstances are as we have set them up. V is AT, so the quantity V squared is the quantity AT squared, which is A squared T squared. GH. Isn't H VIT, you know, H is equal to VIT plus 1/2 AT squared. H equals VIT plus 1/2 AT squared. We know that from our kinematics. I told you this thing started at 0, so that's not an issue. So 1/2 AT squared is going to be what the H is. In place of H, you put 1/2 AT squared. 2 times 1/2 is just AT squared. The G stays. GAT squared. So finally, we're here. We're not done, but we're really close to done. And like I said, T is kind of an arbitrary phenomenon. T is arbitrary in the sense that we decided to take a snapshot after a time T. After a time T, this guy rose a height H. This guy moved over a height H, forgive me, this rose a height H after a time T, this moved over a distance H, and this fell a distance H after a time T. After a time 100 T, we got different things happening here, guys. After a time 100 T, this thing's gonna, you know, it's gonna be going literally, if you look at the mathematics, if it's 100 times more than that, that's an interesting question. If it's 100 times more than the small t we were talking about, if this is 100 T, when you square 100 T, it's not T squared, obviously. T squared is T squared, but the quantity 100 T squared is 10,000 T squared. It's going to go 10,000 times the distance. It's going to be 10,000 H. If the pulleys are big enough and everything's, if the ropes are big enough, everything else, this will be 10,000 H. This will be 10,000 H, and that'll be 10,000 H. That's a long time to fall. Yeah, I mean, you decided to, you know, it's 100 T, 100 times longer. Yeah, if it's 100 times longer, V's going to be 100 times more than that. V's going to be 100 times more than that. Why is that? Because V is AT. It started at 0. Remember, VF equals VI plus AT. Yeah, well, this one's 0, so it's just AT. After 100 times more than that, it's going to have 100 times the magnitude velocity. Interesting point in its own right. So we're looking at this. Let's at some point, I guess I got to erase some of this, guys. But you got it. I mean, you got it on there. Let's see how this plays out. I think the big thing here, you look at this really carefully, and let's get down to business. Let me see where we're going to go with this. Yeah, I mean, there's a number of ways we can go here, I guess. I'll tell you what I'm going to do. Let me take this last equation right here and divide by AT squared on each side. All right, guys, I do have to erase, I think. Okay, so we got this. Okay. Try to get rid of this. This was somehow a little, this particular, it just artistically, I guess you could say, if there's some kind of artistic license, it was just too close to one another. It might be a little confusing. This from here just jumps right to here. I mean, this is one, you have a 1/2 right here. And you got a 1/2, you got a 1/2 right here, and the 2 ain't there. You multiply by 2 on each side, and you're here. Okay, so you guys are all right with that. We got that. Let's look at that last thing. I don't know, I'm looking at it. Let's make it pretty easy. Let's just divide. Let's divide by AT squared. Not the quantity AT squared, just single A, not raised to any power other than 1, and then here's T squared. Let's divide by AT squared on each side. So what happens is, let's take a look at it. Well, the A and the A squared cancel, leaving an A here. The T squareds completely cancel. This is already well, you know it. You know what I'm about to say, guys. You're looking at it. Yeah, you divide it by AT squared on each side. The AT squared is gone. The G remains right here. One of the A's remains, but the T squared's gone. Wow, accidentally, this looks very, 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 very familiar. See, we didn't really mention how long. Now, we could solve for how long it took to fall. It's another matter in its own right. I mean, you got the G right here. Well, I don't need to do that without friction, you guys. Without friction, this guy, there's no work done without friction. That guy's out of there. Then the mathematics comes down to mu sub k m2 is not present. It's just m1. Well, you know where it is. It's just m1 minus m3. And then the whole thing means, if you want to find that, it's going to be a greater acceleration. And you can use the other equations that we had to solve this. But that's pretty fascinating stuff. Notice, now nobody said to you, I mean, hey, look, man, by the way, this thing fell a distance h equal to 100 meters. How long did that take? It's a good question. You know, now we did this, and like I said, we did the mathematics. Might as well, let's see where it was, guys. Let me make sure I don't make a mistake here. I'm pretty confident I got it right here. Just in case, though, let's just kind of look at it. Right. At the end of the day, with the stuff they had in there, you know this. I mean, we've been here. This is the one that didn't have any of the... That's the whole song and dance at the end of that thing. Interesting. We did it in a different manner, and we still got the answers that we want to get. Now, I might want to ask you, hey, man, this thing fell 100 meters. Well, h is VIT plus 1/2 AT squared. Yeah, that's true. We just said we said this thing, the VI was 0. H equals 1/2 AT squared. Do you want to know? I mean, hey, look, I'll tell you something. This thing fell. This process took place for 100 seconds. What's H? What is the amount of fall down? The amount of fall down, my friends, is also the amount of lift up. It is also the same amount of slide over. The slide over through friction on, the mass, friction having to be overcome across the table, it slides across the table in amount h. The one on the far left fell that same distance h, and the one on the right climbed that same distance h. Well, what is h? Well, let's say t was 100 seconds. Let's say this took place for t equals 100 seconds. Well, it was 1/2 times 2.31 meters per second, right? Times 100 seconds. Well, that's 10,000. I mean, however this is, we're just going on the fly here, guys, but I mean, 100 squared is 10,000. 10,000 times 2.31 is 23,100. Half of that, right? 23,100, that is 11,000. Would be 20. Let me see, guys. Let me again. I'm just kind of making this stuff up. When I square 100, I got 10,000. That's going to be 23,100. Half of that is going to be 11.55 thousand. So I think it's going to be this. Wow, that's a pretty big time experiment, guys. I mean, if this thing's going to fall 11,550 meters, that's more than 11 and a half kilometers. Let's say this thing was huge. You designed this huge situation here to see what would happen, assuming the gravitational field stays the same as is. Somebody could turn around and say to you, well, I already know how far it fell. You know what I mean, kind of thing. I already know this thing fell. This thing fell. Let me kind of purposely make this easy. Let's say somebody told you, I know it fell 231 meters. How long did it take for that to happen? Well, wait a minute. H is equal to 1/2 AT squared, right? And you got, 2 times H over A is equal to T squared. So square root both sides. 2H over A. T equals, well, we just said this was 231. 2 times 231 over 2.31. That's 100. T is the square root of, that 2.31 into 231 is 100. 2 times 100 is 200. The square root of 200 is about 14.14 seconds. I mean, there's a lot they could ask you. You've got to be comfortable with this stuff at some level to nail this, to be able to get this thing to work. Okay? Again, fascinating how the consistency of the whole thing works out at the end of the day on this thing. You got, we had it, and we know what the conclusion is. I mean, like I said, if you're not overcoming friction, it changes a little bit, but it changed a little bit last time, and it's a very predictable way it's going to change. M1 mu sub k M2, M1 minus mu sub k M2 minus M3 yeah, and that's giving us the conclusions we're used to seeing. Okay. All right, guys, thanks. We'll see you soon.